Now, before we begin section 5.3, I thought you might appreciate this comic strip. Perhaps after your last test you felt like this young lady in her dream. I will tell you, these are not just random things that the artist has written down. These are actual calculus problems. The first one here is some limits. We've done limits. We've done summations. Here are some derivatives, and then we get to the ever-popular triple integrals of Calc 3. All of these, if you want to look at the door of my classroom, do have the solutions listed. I have worked them out just to show you that it can be done. 5.3, definite integrals and antiderivatives. Our objectives, our standards for today, we are going to utilize properties of definite integrals. Not a huge standard on the AP exam anymore, but still from time to time it will pop up, so we'll talk about that. Calculate the average value of a function. That is a huge objective, a huge standard, not only just for the average value within themselves, but for the applications thereof. And then we'll hit the mean value theorem for definite integrals. We'll also talk about differential and integral calculus, how we bring those things together. Hopefully you can see the whole screen okay. Let's begin. Alright, we'll slide the screen up here. If I can get it to move, there we go. Rules for definite integrals. As we go through our work with integrals, and there will be many things that we do, there are going to be certain properties that I'm going to refer to, certain tricks and shortcuts that we come to that will help us out. The first is called order of integration. Now if we look here at the first one, integral from a to b, f of x dx equals negative, b to a equals negative integral a to b f of x dx. You see, this is what we're used to right here. Start at a and go to b. You see how the limits have been flip-flopped. Here's from a to b. This one's from b to a. Doesn't matter which one's bigger. The number on bottom is the number where you're starting. The one on top is where you're ending. The difference between these two things is a negative. If you flip-flop the order of integration, it changes the sign of the integral. Alright, next we have the zero property for definite integrals, which is very simple. The integral from a to a of f of x dx equals 0. If you're starting at a and you're ending at a, there's no base width for your rectangle, so the area would have to be 0. Constant multiple rule, we've had this for derivatives and for limits. It also applies for integrals. If you have a constant multiple in here, that multiple can be taken out, whether it's a positive or if it's a negative. Sum and difference rule, just like for limits and derivatives. If you have an integral that's broken up or is the combination of two parts, whether they're being added or subtracted, you can break it up into two separate integrals, and sometimes that is easier to do. Alright, the rule of additivity. The integral from a to b of f of x plus b to c of f of x is a to c of f of x. Which, if you think about it, makes perfect sense. I mean, here we're starting at a and we're going to b. This one starts at b, right where we left off right here, and goes to c. So we could just put both of those things together and just have this one lump integral from a to c. Then we have the max and the min inequalities. If max f and min f are the maximums and minimums of f on AB, then we have this. Now this rule here stems a couple sections back. Remember when we did the constant, there was a rule where we had, if you're taking the integral of a constant, and that constant was c, we said the area was c times b minus a. Well, what if we assume that c value to be the minimum of f? Well, the minimum of f would imply everything else is above it, right? Well, if that's the case, then the integral, which includes everything else above it, would be bigger here. But the max, then, we would assume would be everything above, so f of x would all be below, which means the integral would be below. And this makes perfect sense. If you just consider this to be the minimum, that to be the maximum, the integral has to be somewhere between the min and the max. And then we have the rule of domination, which simply says if f of x is greater than g of x for all x in that interval on a to b, then the integral is also going to be. So if you have one function that's higher than another function all throughout a given interval, then their respective areas underneath those curves are also going to follow that same pattern. F is greater than g. Now in a very specific fashion, if f of x is positive on a to b, then, move the screen down here a little bit, then the function here, the integral function you see, is also going to be positive. That is the rule of domination. Alright, so we'll start with example 1. Using the rules for definite integrals, we're going to find each of the following things on the bottom. So we're going to find all these values down here, assuming that these are true. The integral from -1 to 1 of f of x dx is 5. The integral from 1 to 4 of f of x dx is -2. And the integral from -1 to 1 of h of x dx is 7. So we'll start with this one. The integral from 4 to 1 of f of x dx. Now if we look at this here and we compare it to this one up here, what do you notice is the difference? Well, the difference is this one is 4 to 1, this one is 1 to 4. So what do? We change the sign. So instead of a -2, it's a +2. Alright, here we go to this one. When I look at this one, I see the integral from -1 to 4 of f of x. Well, this one starts -1 to 1. This one then picks up where that one leaves off at 1 and goes to 4. So if we go back to our rule of additivity, we can take here to here plus there to there. In other words, I can take 5 plus -2 and I can get 3. Alright, go to the next one. Integral from -1 to 1. So here works and here works. You see the f and the h both have those same limits of integration. And this one tells us to take 2 times the f answer plus 3 times the h. Well, the f answer was 5, so it would be 2 times 5 is 10. The h answer is 7. 3 times 7 is 21. 10 and 21 make 31. Now we come down here and we have the integral from 0 to 1. And what I hope you notice is that these use limits of integration that are not dealt with up here. There's nothing up here that gives us any kind of information about f going from 0 to 1. Therefore, on this one we say there is not enough information. NEI, not enough information. Sorry for my laziness there, but I didn't want to type all that out. NEI. Alright, then we go here, h of x, -2 to 2. Now what some people will say on this one is they'll say, well, -1 to 1 is 7, so -2 to 2 must be 14. But you're assuming a symmetry for h that we don't necessarily know is there. Maybe h, while it is equal to 7 here, maybe it jumps up a whole bunch after -1 and 1, or maybe it goes to 0, or maybe it does different things on the ends. We don't know. But as we don't know, again, we have to say not enough information. And now last we do -1 to 4 of f of x plus h of x. Now we can do -1 to 4 of f of x. We've already done that, haven't we? That was 3. We did that one up here. But again, there's no information given about h of x, about what it does once it leaves 1. There's nothing about from 2 to 4 or 1 to 4 or anything up here for h of x. Therefore, we again say not enough information. Pay very careful attention to your limits of integration. Many times that will give away the problem if you can't work the problem, if there's not enough information. Alright, let's move our screen here a little bit. Finding bounds for an integral. Our job here is to show that the value of the integral below, this integral right here, is less than 3/2. Now, obviously, the simple way to do this one, if we were doing this on a test, would be just to punch in this into our calculator, find the integral, and then we would have it proven. But let's assume this is on the non-calculator portion of the test. We can still do this. The first thing we know is this. If you were to sketch the graph of this function, now when you go to sketch the graph, don't sketch the graph in the integral part. Just sketch the graph of square root 1 plus cosine x. What you'll find when you sketch the graph is that the maximum value of the function occurs at 0. You'll see that that's the highest point on the graph. If you want to pause the video now and check that out, you can. That's the highest point on the graph, and then it drops after that. So that gives us our maximum value. Alright, and if we plug in 0, then we see that the maximum value is radical 2, which is about 1.414. Hopefully that's a radical that you remember and recognize. Now, from the maximum rule that we had, we know that if this is the maximum of the function over the intervals 1 to 0 or 0 to 1, then the integral itself must be less than the maximum value here. Well, 1 minus 0 is 1, and 1 times 1.414 is 1.414. And remember, we wanted to show that it was less than 3/2, and 3/2 is 1.5. Move the screen down here. And you see that we have now, we've actually shown that not only is it less than 3/2, it's actually less than 1.4. Alright. Average mean value. Let me back up a little bit before we do that. If f is integrable on a closed interval AB, its average or its mean value on that same interval is found by doing this. Now, what you'll notice here is we do have this integral from a to b of f of x dx, which is the area, the total area underneath the curve. But what we do to get the average, if you think about what average is where you take the total amount and you divide by the number of things that you have. Well, how many spots are there between a and b? Well, to find that, we just do b minus a, the second number minus the first number. And so here we have the total amount divided by the number of things, and that gives us the average. Alright, so using that formula, let's find the average value of f of x equals 4 minus x squared on the interval 0 to 3. And does f actually take on this value at some point in the given interval? Well, let's see. So we set up our problem. 1 over b minus a, 3 minus 0, integral from 0 to 3 of 4 minus x squared dx. Alright. Sorry, I'm going to move the screen here a little bit because we're going to need it at the bottom. Now this integral from 0 to 3 of 4 minus x squared, you could work out using antiderivatives and all, but really, or what I would just suggest doing is punch this into your calculator. You can do this integral from 0 to 3 of 4 minus x squared using the template functions on your calculator. You know how to do that. And that works out to be 3. 1 over 3 minus 0 would be 1/3. So therefore, the average value is 1. And then it says, does f actually take on this value at some point in the given interval? Well, to figure that out, let's take our function 4 minus x squared and let's set it equal to 1 and solve. So we'll subtract our 4 over, divide everything by negative, x squared equals 3. Take the square root, x equals plus or minus radical 3. Now the question is one of those two values in the interval 0 to 3? And yes, radical 3 is in that interval. And this is a perfect lead-in to the mean value theorem for definite integrals, and you see it is starred. This is the next theorem in our big 7 theorems of calculus. If f is continuous on AB, then at some point C in AB, this must be true. Now this is very, very similar to the mean value theorem that we did for derivatives. Remember, for derivatives, we didn't find the total area under the curve. What we found was the secant line connecting the endpoints there and there, and we said that there was some point C that if you found the tangent line at that point, you would have the same slope as the secant line. Integrals, it's a very similar process. If we were to find the total area underneath this curve, and just imagine this blue part right here being right here, that total area, then there is some point C that takes on that value, takes on that average value. Now what that means for us graphically is that there's some point C where if we were to draw this horizontal line right here, we could make a perfect rectangle for the area underneath, including this part right here, and this part right here would match perfectly what's up here. Okay? So where is this useful to us? Well, let's see. How long is the average chord of a circle? Let's work this one out. Suppose we have a circle radius r centered at the origin. That's what we have right here. We want to know the average length of the chords. Now, if you don't remember, chords start on the edge of the circle, go to the next edge of a circle. So what is the average length? If I were to draw every single chord, every single chord on the circle, what would be the average length? Well, how are we going to do this? First of all, we're going to show that the length of a chord is this. Just if I were to just draw some generic chord, its length could be described by this equation. Now, how do we do that? Well, here's what I know. I know that the upper hemisphere, this top blue part right here, can be represented by this equation. Now, how do I get this equation? Well, imagine the equation of a circle, x squared plus y squared equals r squared, r being the radius. And then if I take that equation and I solve for y is equal to the square root of r squared minus x squared. And so that is the upper hemisphere here. The lower hemisphere is the exact same thing, only it's inverted, so I will put the minus sign on them. And then I combine the two together, that minus that, because isn't that what distance is? You do top minus the bottom. And when I do that, it gives me this. Now my first recording is about done, so we'll take just a very